October 9th. Wow, almost, but not quite. So let's talk about the fundamental theorem of calculus, and we'll talk about both parts. So again, part one really just says that the derivative of the integral equals the function you started with. I know we said this last time, I'm saying it again. The derivative of the integral from a constant to x of some function, usually of t, although any other variable except for x is totally fine to use there. The derivative of the antiderivative is just the function you started with. We did a number of examples last time where we did it the long way, we did it the short way, and we saw that every time, oh yeah, you get that. And then the more general version of this rule is that the derivative, I'm actually going to give you the very, very general version, is that if the lower bound is some function of x, and the upper bound is also some function of x, of f of t dt, you still get the same result. You still get the inside function, except you're evaluating the inside function at your limits of integration, and the chain rule applies. So you have to end up multiplying by the derivative of those limits of integration. So you're going to be getting the top thing, f of, instead of f, h of x times the derivative of h of x minus, and then the same thing happens. You get f of g of x times the derivative of g of x. So these are the simple version and the very, very general version of the first part of the fundamental theorem of calculus. For example, we could be asked to find the derivative of the integral from x cubed to natural log of x of, sure, secant squared of t dt. And the whole point here is to not do more work than you need to do. Really, I mean, okay. The whole point really is understanding that the derivative of the antiderivative is the original function. But after that, the point is not to do too much work. And the way we don't do too much work is by applying the theorem. Say, oh, yeah, I know the derivative of the antiderivative of secant squared of something is secant squared of something. But the something is now first the natural log of x, and then we multiply by the derivative of the natural log of x. And then we subtract, and then we do secant squared of x cubed, multiplied by the derivative of x cubed. This is the way you should answer a question like this. However, occasionally on an assignment, they might make you go through, jump through some hoops and make you do it the long way by first finding the antiderivative and then taking the derivative of it. So just to show you that one more time, if we first just took the antiderivative, ignoring the derivative here, so if I did this part first, the antiderivative from x cubed to natural log of x of secant squared of t dt. Well, if you look at that little chart I just handed out, the antiderivative of secant squared is tangent of t. So we get tangent of t, evaluated from x cubed to natural log of x. It's always from the bottom to the top. And then we're going to plug in, we plug in the top first. It's a tangent of natural log of x minus tangent of x cubed. And the homework problems you're doing might say like, this is g, like they might say that the integral is g of x. And then you're trying to find g prime of x. So they might say this is g of x. And then we're going to find in part two, g prime of x by literally just taking the derivative of this. That's going to be the derivative of tangent of natural log of x minus tangent of x cubed. Oh, yep. I was just about to be like, I probably am off. Oh, I can see it over here even. Okay. Unsurprisingly, the derivative of tangent of some stuff is secant squared of that stuff multiplied by the derivative of the inside stuff minus the derivative of tangent of x cubed is secant squared of x cubed times the derivative of x cubed. The same exact answer. That's the whole point of doing it both these ways, is to see that whether you do it the long way or you do it using the fundamental theorem of calculus part one way, you get the same result. So why would you do it the long way? Also, sometimes you can't do it the long way because sometimes the function cannot be anti-differentiated. Questions about that? All right. Let's talk about the second part of the fundamental theorem of calculus. Let's keep your notes in order here, James. So, fundamental theorem of calculus, part 2, also known as the evaluation theorem. The very short answer, or the very short expression here, I don't know, there's words I'm looking for that I'm not writing. The thing we're going to say here is that this just tells us how to evaluate a definite interval. So it tells us that if you're trying to find the integral from a to b of f of x dx, it is equal to the antiderivative of little f, which we often use a capital F for, evaluated from a to b. You might write this also as capital F of b minus capital F of a, where we do need to at least somehow say where we know that capital F of x is the antiderivative of little f of x. I know I said different words than I wrote there, but they mean the same thing. So capital F of x being the antiderivative of little f of x means exactly the same thing as the derivative of capital F equaling little f, right? This is equivalent to the antiderivative of little f of x equaling capital F of x plus c. But this is the more evocative notation. What do I want to say about this? You might ask, trying to think about this for a second here. You might ask why this is true. There is a way to prove it. It's kind of super annoying. And I'm sorry, my brain is kind of like, oh, why is this true again, James? You know why this is true. Yeah, good job. Oh, I know. Oh, yeah, of course. Okay. So I'm like, I know how this works, I think. So we know that the antiderivative of f of x is the antiderivative of f of x, but there's like this plus constant thing, right? So we definitely know, yeah, I need to draw a picture. I'm like, I know I'm doing something here. So here's the idea. There's A, there's X. We're going to call this area under the curve. Sometimes people call it capital A of X just to kind of help us see what's going on here. Where X is variable, A is constant. So you can think about like moving X to the right and the area getting larger, moving X to the left and the area getting smaller. So we're going to say that capital A of X is the area under the curve from A to X of f of t dt. I'm going to use f of t. Okay. So then a couple things. Like, so, sorry, my brain is a little bit like, I know you're supposed to know how to do this. So I want to point out that certainly we're saying that the f of x plus c is an antiderivative. Sorry, that looks terrible. Of little f of x. And we can think of this as being just equal to some f of x plus c. So how do we know exactly what we're going to get when we try to calculate this here? Well, let me ask you an important question. What's the area under the curve from A to A? If you start at A and end at A, how much area is there? Right, it's equal to 0, which we can think of as the antiderivative, capital F of t, evaluated from A to A, which is f of A. I'm sorry, I'm like, my brain is kind of blowing right now. It's okay. So I know what I'm trying to say, but the words are not coming out very well. The thing I meant to say here is that this is equal to 0, but we also know it's equal to essentially, oh yeah, it's okay. It's equal to f of x plus c. F of A. There we go. There's the magic. Okay, sorry. All right. So we know that this antiderivative is f of x plus c. And then specifically, if you plug in a for x, we know we get 0, which is equal to f of a plus c. So that's going to equal, or that's going to show us that f of a is equal to, sorry, negative f of a is equal to c. Apologies, that's the worst way you could have done that. But you can see that even though I subtracted in the wrongest way possible, negative f of a is equal to c. Here's where I'm trying to get to in probably the least helpful way I've done in the past. So if I'm trying to figure out, if I'm trying to say that the integral from a to x of f of t dt is equal to f of x plus c, I'm going to replace x with b and get that the integral from a to b of f of t dt, well, it's not f of x anymore, it's f of b plus c, but we just saw that c, in fact, is equal to negative f of a. So that's how you can kind of justify using the second part of the fundamental theorem of calculus using the first part of the fundamental theorem of calculus. There's also a much, much, much longer proof of this where you like add up a bunch of rectangles and show that you end up getting capital F of B minus capital F of A, which we're not going to do because it's terrible. But that's the general idea, is that if you're trying to find the value of a definite integral, we take the antiderivative of the inside function and we then evaluate it at the endpoints. I know we've done this already many times, but now I'm actually saying the words. So for example, to find the area under f of x equal to x cubed plus e to the x on the interval from 0 to 2, we simply calculate the antiderivative or integral of x cubed plus e to the x dx from 0 to 2. This, by the way, is why we use this notation, this long S symbol, both for the area under the curve and for the antiderivative, because they're very intimately related to each other. Finding the area under the curve, we do by taking the antiderivative and then plugging in the endpoints. So it makes sense to use this notation for area under the curve. And just as an aside here, this notation for the antiderivative. The difference being this is a definite integral, and when we find our final result, the answer is going to be a number, some area, some net area under the curve above the x-axis. It could be positive, it could be negative. Whereas this answer over here, if you're asked to find the indefinite integral, aka the antiderivative, it's going to be a function. So indefinite integrals or antiderivatives are functions. Definite integrals are numbers or areas. So calculating this, it's going to be x to the 4th over 4 plus e to the x, evaluated from 0 to 2. Plug in the top limit first, you get 2 to the 4th over 4 plus e to the 2nd. Subtract, plug in the bottom limit, you get 0 to the 4th over 4 plus e to the 0. Simplify, or don't, depending on what you're doing. If you're plugging this into web work, you can just toss that in there and it'll take it just fine. But if you're simplifying, we're going to get 2 to the 4th, which is 16 over 4, plus e squared, minus 0, minus 1. So that's 4 minus 1, so I get 3 plus e to the 2nd power. And that is the simplest answer you can get. It does not get any simpler than that. You should not get a calculator out and find a decimal approximation. I don't want to know that it's approximately 10 point something. I want to know that it's 3 plus e squared. And so does your teacher, right? They don't want you to, unless they say, give me a decimal approximation, you should always stop at e squared or pi to the 3rd or whatever your terrible irrational number is to some power is. Cool. Okay. Time flies in this class. All right. So we'll talk more about area under curve, area between curves. I don't think we've quite gotten there yet, but I felt like it was an opportune moment to give an example. But or at least we haven't gotten there fully with definite integrals. Let's work our way around or back to just talking about antiderivatives. So we've talked about kind of the basics of antiderivatives already, right? That any function you know the derivative of, you know the antiderivative of that derivative. Like all the trig functions, like e to the x, like natural log of x as a derivative of 1 over x, and the antiderivative of 1 over x is the natural log of the absolute value of x. I think that's kind of the whole list. Oh, there's a couple other things, right? Like we should know that the antiderivative of 1 over x squared plus 1 is good old arctangent of x plus c. The area under the curve from 0 to 1 of 1 over, I know, I said I lied, sorry. I want to do another area question. The area under the arctangent function, sorry, the area under the function 1 over x squared plus 1 from 0 to 1, which looks kind of like this. If you plug in 0, you get 1. You plug in 1, you get 1 over 2. And you get smaller as you go to the right. It looks vaguely like that. There's the left half of your arctangent function. Sorry, of your 1 over x squared plus 1. Maybe I should label it. That's a good idea. Of your 1 over x squared plus 1 function. There's the left half, and the right half is just, sorry, there's the right half. The left half, my God, let me slow down a little bit. There's the right half, there's the left half. I want the area under this curve from 0 to 1. So it should be all that. So it's just going to be the arctangent of x evaluated from 0 to 1. Useful thing to know when you're finding a definite integral, aka an area under a curve, you don't need the plus c. You can write it, but if you write it, it's just going to be canceling out with itself. Because you would write arctangent of x plus c. Right, you could do arctangent of x plus 7. I decided 7 was the number I wanted from 0 to 1. And then you're going to get arctangent of 1 plus 7 minus arctangent of 0 plus 7. And the 7s will cancel, or the c's will cancel. So you never need the plus c for a definite integral. So here we would get the arctangent of 1 minus the arctangent of 0. And then we are expected to be able to simplify this. We're supposed to know that the angle whose tangent is equal to 1 is pi over 4. Always radians, never degrees. And the angle whose tangent is equal to 0 is 0 radians, also 0 degrees. So we get pi over 4 units of area. Kind of neat. Okay, but back to the topic at hand, which is just antiderivatives. So regular functions are fine, but then they get more complicated. And that's kind of what a lot of antidifferentiation is really dedicated to, is how do we deal with functions that are more complicated than just something that is easily recognizable as the derivative of something else. For example, what if I wanted to find the antiderivative of, let's make it easy, 4x cubed times x to the 4th plus 1 plus, sure, 1 squared. Depending on how algebraically complicated it is, you might be able to just multiply it out. And we certainly can here, which we're going to do first just to see how this might work. So if we multiply it out, do that the first way, I'm going to get 4x cubed times x to the 4th plus 1 squared is x to the 4th squared plus 2 times x to the 4th times 1 plus 1 squared, which is x to the 8th plus 2x to the 4th plus 1. And then we're going to distribute the 4x cubed to each term. So we're going to get the integral of 4x to the 11th plus 8x to the 7th plus 4x cubed. I'm still writing the integral symbol and the dx because I haven't done any antidifferentiation yet. I still need the instructions telling me what to do if I haven't done the thing yet. And then I'll just remind everybody that all you should think of when you see these two things are those are just instructions telling us to antidifferentiate. And the dx is telling us what variable we are antidifferentiating. If it was a dy, we'd be antidifferentiating with respect to y, and so on. Later on, in 17C, when we talk about functions of two variables, this actually becomes a little bit more important because sometimes you'll have like a double integral with a dx and a dy, and then you have to pay attention to which variable you're integrating first. And for now, the variable the x variable there in the dx should match the variable in your integrand. So We're going to anti-differentiate each thing. I'm going to get 4x to the 12th over 12 plus 8x to the 8 over 8 plus 4x to the 4th over 4. Yeah, plus c, why not? You could probably skip that step and simplify, right? I definitely would have been written just as x to the 12th over 3 plus x to the 8th plus x to the 4th plus c. Okay. I want to point that out. Yeah, that's fine. Sure. Okay, so now we're going to go a different way. We're going to do what's called a u-substitution. So when you're doing a u-substitution, what you're really doing is you're trying to identify or trying to undo a chain rule, kind of. You're trying to figure out what function you could take the derivative of using the chain rule that would end up with this. So really your job is to kind of identify the inside of the function that you end up multiplying by the derivative of when you would take the chain rule. So here, an excellent candidate for the inside of the function is x to the 4th plus 1. Because it satisfies the two criteria we're looking to satisfy. One, the less important one, that is inside something else. Here, the x to the 4th plus 1 is getting squared. That's usually just a good way to that's a good way to make a guess of what you might want. Like, oh, I see something inside some other function. That's probably a good choice for you. The more important part is that we really, really want its derivative to also be in the integral. And it is. If we take the derivative of u with respect to x, it's going to equal 4x cubed, which is exactly the other piece that's in the integral. And we're very happy about that. Most people usually skip saying du dx equals the derivative and simply isolate the du on the left and the derivative times dx on the right. Those are the differentials. In this case, we don't have to do anything else with our du dx relationship here because we exactly have 4x cubed times dx in the integral. So you don't have to do this. By often, at least the first time, like to rewrite my integral so all the things that are next to each other are next to each other. So I'm going to rewrite this as the integral of x to the 4th plus 1 squared times 4x cubed dx. And I'm going to observe that, oh, look, 4x cubed dx is exactly equal to du. I think I said this last time, probably, it's always important to make sure that the dx du transformation happens first. Ignore everything else until you've dealt with making sure the dx turns into du. And then x to the 4th plus 1 is our u. So we're going to rewrite this integral. We're going to translate from the language of x to the language of u and get the integral of u squared times du. We still have to anti-differentiate after we've translated it. So there's still an integral symbol there. It's still telling us to find the antiderivative. Apologies, I'm going to go back and forth between integral and antiderivative. They're just so interchangeable in my mind, and they will be in your mind, that when we say integral, antiderivative, we really just mean the same thing. If we're talking about area, I'll try to say definite integral, but I'll probably just say integral as well. So get used to hearing both of those and thinking, oh yeah, we mean the same thing there. The antiderivative of u to the second is u to the 3rd over 3 plus c. It's a little loud back there. If you guys could whisper a little quieter, it's all right. I'm hearing it. It's just making it harder for me to hear what I'm saying. So then u cubed, I then have to go back to the variable I started with. So I'm going to plug back in what u is equal to and get x to the 4th plus 1 cubed over 3 plus c. So now the big question, are these the same? Did we do the right thing? Well, they don't exactly look the same. Let's multiply this one out and see. Also worth knowing, when you cube something, like a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. If you're interested in how I do that so fast, come ask me about Pascal's triangle sometime. So x to the 4th plus 1 cubed is going to be x to the 4th cubed plus 3x to the 4th squared times 1 plus 3x to the 4th times 1 squared plus 1 cubed all over 3 plus c. And I'm running out of room, but I'm going to make it simple. So simplifying this, sorry, I know it's terrible to, let me just give myself some space over here. I get x to the 12th over 3. I get 3x to the 8th over 3, which is just x to the 8th. I get 3x to the 4th over 3, which is just x to the 4th. And I get 1/3 plus c. Are they exactly the same? Thumbs up for yes, thumbs down for no. Exactly the same. They're not exactly the same. But are they the same enough? Yes, they are. So as long as whichever way you did it resulted in integrals that differ by at most a constant, we're good to go. Because either way, whether you take the derivative of this, x to the 12th over 3 plus x to the 8th plus x to the 4th plus c, or the derivative of this, the same thing plus a 1/3 plus a c, the derivative is still going to be the same. So as long as they only differ by a constant, we're fine. There are some integrals later on where you can integrate them either by like doing a u-substitution or by doing some polynomial division. And depending on the way you do it, sometimes your answer does look slightly different based on the method, but it's still going to be the same if we've done the right things. So, oh yes, question.
Just to see, when you get u squared times du,
Yes.
how do you get divided by 3 with 3?
So how do we anti-differentiate our variable to a power? No, that's all right. So, right, it's just the anti-power rule, which is just u to the 2 plus 1 divided by the new power plus c.
Thank you. That makes sense.
Good. So this is, and now I will point out, I wouldn't actually multiply this out if I had done it as u-substitution. I would leave my answer as x to the 4th plus 1 cubed over 3 plus c. That is the correct way to write the answer here. We should not multiply it out. We were only multiplying out to see that we ended up with the same thing. So this is the very general idea of a u-substitution, but the thing about u-substitution is while sometimes you could do it this algebraic way instead, a lot of times you can't or you really wouldn't want to. For example, if I was trying to find the antiderivative of x cubed times x cubed again, James, are you so unoriginal that you picked? Yeah, let's make it a little bit better. X to the 13th times x to the 14th plus 7 to the 99th power. While it is technically possible to multiply x to the 14th plus 7 to the 99th power, you're going to get 100 terms, and it's going to take you forever. It's going to take me forever, right? At that point, you're using a computer, and if you're using a computer, you should just be using it to find the integral in the first place. So we don't have to do that, though, because there's a very nice u-substitution here. There's an excellent choice for u. It's the stuff inside the other function. So I'm going to pick u equal to x to the 14th plus 7. And then the first thing I do if I'm ever trying a u-substitution, I say I'm emphasizing trying there because later on we might try a u-substitution and it might not be the right thing to do. But it's almost always the first thing I'm going to try to do because a u-substitution is kind of the easiest thing to do as far as our methods of integration. So it's always good to try u-sub, and then if it doesn't work, do something else. So after picking what I think u should be, I'm going to write down that du is the derivative 14x to the 13th power times dx. I skipped the step of writing du dx equals 14x to the 13th power. People differ as to how they like to do this. There's probably 3 technically different ways to go through the next steps that are all just as good as one another. My preference is to make whatever I have on the right-hand side here look like what I have in my integral. So I would notice in my integral that I have x to the 13th times dx. I don't have a 14, so I'm going to divide both sides by 14. That's a perfectly fine way of doing it. And say that 1/14 times du is equal to x to the 13th times dx. So I would choose to rewrite this integral as the integral of x to the 13th times dx in red gets replaced by 1/14 times du. And then the x to the 14th plus 7 gets replaced by u. So I have u to the 99th power. Before I finish that, though, I'm going to point out 2 other ways you could do it. I will almost always default to doing it this way because it's what I like. But you alternatively could do this. Some people like to just isolate dx, and there is a time and place for that. Now is not, in my opinion, the best time. But you could say dx is equal to du divided by all of that. and then start by replacing dx with just that. So doing that way, you could write this as the integral of x to the 13th times x to the 14th plus 7 to the 99th power times du over 14x to the 13th power. I don't like this personally because I don't like having x's and u's in my integral at the same time. It feels incorrect to me. It's fine. I don't have to like everything. But then notice that the x to the 13th divide to 1, and then you can replace the remaining x to the 14th plus 7 with u, and we get exactly to the same spot. We get exactly u to the 99th power times 1/14 times du. Yes, I would put the 1/14 in front of the integral. I just haven't. So that's another way of doing it. And then thirdly, if you prefer, this one I really don't prefer, you could try to make the integral look like what you have here. So you could say, oh, I really wish I had a 14 times x to the 13th. So just do that. Say my integral of x to the 13th times x to the 14th plus 7 to the 99th power dx is equal to 1/14 times 14. I didn't really change anything. I just multiplied by 14 over 14. X to the 13th times x to the 14th plus 7 to the 99th power dx. And then the part I'm about to underline, that's my du. And then I get the same thing again. I get 1/14. In red is my du. And then here I'm left with, again, u to the 99th power. So whichever way you slice it, you're still going to get to the same place. I don't care how you do it. I just care that you do it in a way that works for you, that's correct. People often tend to like doing it this way. It's usually fine. Occasionally it can be dicey. Occasionally it can be dicey if the u-substitution like isn't a nice one, or like you pick it, you're doing a u-sub, but your du isn't there perfectly or perfectly up to a constant. And then doing it this way is not really the right way to go usually. So I usually default to this. I should also point out, when I said u is equal to x to the 14th, I was looking for my du to be in my integral. And when I say that, what I'm really saying inside my head is I'm looking for a multiple of my du to be in my integral. I don't care that I was off by a factor of 14. I can always fix being off by a factor of a constant multiple, which we just did. So then we would rewrite this. You don't really have to rewrite this as 1/14 integral of u to the 99th. It's just, I would have probably already brought out the 1/14 before I did any of this. And then we're going to get 1/14 times u to the 100th power divided by 100 plus c. We're going to simplify as whatever u is to the 100th power over 1400 plus c. And we're going to replace u with x to the 14th plus 7. So for indefinite integrals, aka antiderivatives, your answer is a function or a number. Function. And if your answer is a function, it has to be using the same variable we started with. So if your integral originally starts with the variable x, your antiderivative has to end with the variable x. So you always have to plug back in what x is equal to figure out, or what u is equal to in terms of x to find out the actual antiderivative. All right. You also try one. Sure. Try. Try the following. Try. I want to make. Yeah, sure. So I'm trying to think about x squared square root of. Sure. 2x cubed plus 7 dx. Try thinking about what a good choice for you would be. I bet you all know what it is. I suppose I should also say, if you're ever waffling on a choice for you, you always want to pick, if you have the choice of like picking the plus a constant or not picking the plus a constant, it's usually good to pull the constant along. Like I'd much rather pick u equal to 2x cubed plus 7 as opposed to just 2x cubed. You want all the stuff inside the function. You want all the stuff. No, I said the same thing. You want all the stuff inside the function because adding a 7 doesn't change the derivative. Those are the choices I would make. I would choose u equal to the entirety of the argument of the square root there. So u equals 2x cubed plus 7. My du is 6x squared dx. I'm happy that my du has x squared times dx. I get rid of the 6 by dividing both sides by 6 or multiplying both sides by 1/6. And then I'm going to rewrite my integral as 1/6 du, putting the 1/6 out in front because we always can put that constant multiple out in front. And then we have the square root of u, which we should definitely rewrite as u to the 1/2. So 1/6, the antiderivative of u to the 1/2 du. We anti-differentiate u to the 1/2 in the usual anti-power way by adding 1 to the power and dividing by the new power. And then slapping on plus c. We should definitely simplify that. So here's what usually happens when you have a fractional power that you've added onto. You're going to get 1/6 times, leave yourself some space. 1/2 plus 1 is 2/3. Whoa. 1/2 plus 1 is what? 3/2. I was jumping ahead to the next part. And then dividing by 3/2 is equivalent to multiplying by 2/3. So we usually just skip the writing divided by a fraction and instead multiply by the reciprocal. And then we should simplify that coefficient. 1/6 times 2/3 is 1/9. And then we have u, which is 2x cubed plus 7 to the 3/2 power. Let's see. Nice. Something here. So let's look at a few more things. We got time. We might as well just do a few more substitutions here. Sorry, I feel like I got away a little too fast. So another example. What if we want to find the integral of, like, say, 2 over 3 minus 10x? Interesting. So do I have a good choice for you? Well, I would say yes. Because I have something, I often use the word stuck. I have something stuck inside another function. Here specifically, the 3 minus 10x is stuck in the denominator. You could think of this, although I don't usually like to write it this way, but you could think of this as 2 times 3 minus 10x to the negative first. And then it's a little bit easier to see, like, oh yeah, that 3 minus 10x really is stuck inside being raised to the negative 1 power. You can't break it out from there in any meaningful way. So what do we do with this? Well, we're going to do a u-substitution. Also, that 2 is kind of pointless there. It's not pointless, it's not really affecting what our antiderivative is going to be. I would put that 2 out in front of the integral. So I would choose to rewrite this as 2 times the integral of 1 over 3 minus 10x. And I would leave it as a fraction like that, not as a 3 minus 10x to the negative 1, although either way is fine. And then I'm going to choose u equal to the entire thing that's stuck inside the denominator. So the denominators are also often a good choice for you. Everything in the denominator is sometimes something that we choose. And then my derivative is going to be negative 10 times then dx. I want to point out, I've talked about things like this already, where if you took the derivative of the thing, the chain rule would kind of make you multiply by a constant. Right? If you took the derivative of 2 over 3 minus 10x, I know we're not doing that, but if you took the derivative of the entire inside, I know we're supposed to be taking the antiderivative, but if we took the derivative, you would get negative 1 times 3 minus 10x to the negative 2 times negative 10. And so we should start thinking about how the fact that if the chain rule in differentiation would have made us multiply by a constant, then the antiderivative is going to make us divide by that constant. So I know that eventually we're going to divide by negative 10. Which makes sense here because look, we're literally about to divide by negative 10. Negative 1/10 du or du divided by negative 10 is equal to dx. So we're going to start rewriting this. We're going to get 2 times the integral of, even though I really am tempted to write just 1 over u and then something, I'm going to obey my own rules and change dx into something with du first. It is always the best way to do it, I promise you. So my dx turns into negative 1/10, which I could have put out in front, but I didn't, du. And then my 1 over 3 minus 10x is just 1 over u. Most of the time, I would then rewrite 1 over u or 1 over something as u to the negative corresponding power. This is the only one I don't. I don't like writing it as u to the negative 1. It's less easy for me to remember that the antiderivative of u to the negative 1 is the natural log of the absolute value of u. It's much easier for me to remember that when I see 1 over u, the antiderivative is the natural log of the absolute value of u. So here, we're going to get 2 times negative 1 over 10, so negative 2/10 times the antiderivative of 1 over u is the natural log of the absolute value of u plus c. I don't want to simplify that 2/10 just yet, even though I could, just so you all can see what we get. We get negative 2/10 times the natural log of the absolute value of 3 minus 10x plus c. Which, if you think about taking the derivative here, makes complete sense. If you took the derivative of the natural log of some stuff, you would get 1 over the stuff times the derivative of the inside stuff. In fact, why am I saying it when I could write it? If I took the derivative of negative 2/10 times the natural log of the absolute value of 3 minus 10x, I'm really not paying attention to the natural log here. I'm going to get negative 2/10 times, yes, I can. The derivative of the natural log of something is 1 over the something multiplied by the derivative of the something, which is negative 10. And then the 10 cancels the 10, the negative cancels the negative, and we end up getting 2 over 3 minus 10x, like the function we started anti-differentiating in the first place. What I really want to say is we could have done this problem without actually doing a u-substitution. This is what I would also call an example of a mini u-substitution, where the thing we chose for u ended up just being a linear function of x. So for 2 more quick examples, I know we have 2 examples in 2 minutes, no problem. Really, they're going to be quick, I promise. So if I was integrating something like 1 over 5x plus 4, I know that's 1 over a linear function of x. I know the integral of 1 over x is the natural log of the absolute value of x. So the integral of 1 over a linear function of x should be the natural log of the absolute value of that linear function. But, plus c. If we took the derivative of the natural log of that stuff, we would get 1 over that stuff multiplied by what number? Say it loud. 5. But there isn't a 5 there that I'm multiplying by, so I have to divide by 5 so that everything works out okay. Done. That's our answer. I didn't do the u-sub. I could have done the u-sub and it gotten to the same place, but for ones like this that are small, you really don't need to. Another example would be something like the integral of e to the 3x plus 7. I know that if I differentiated that, I would get e to the 3x plus 7 times 3. The antiderivative is going to be e to the 3x plus 7. But instead of multiplying by 3, I have to divide by 3. Also, if you don't like the plus 7, no, I shouldn't say that because it's not really. I got another minute. If I was going to do the integral of cosine of 4x plus 2, it would be sine of 4x plus 2, and I would divide by 4. And that is a 4, believe it or not. Sorry, that 4 looks terrible. That's a 4. So if your choice for u would have been some mx or some mx plus b, what almost always ends up happening is we end up dividing by the coefficient of x. So we end up dividing by that m. Every time here. U would have been 5x plus 4, we divided by 5. U would have been 3x plus 7, we divided by 3. U would have been 4x plus 2, we divided by 4. That is not a coincidence. It is a pattern that you should believe in and use. All right, now it's 2 o'clock. I'll stop talking.